Hi there, this is the video for Chapter 2, Section 3. This section is full of terminology and notation, so be sure you're taking notes somewhere with all these symbols and formulas. Trust me, you'll thank me later. The big concept you're learning today, the mean of a data set, is the basis for all types of computations and statistics, so make sure you understand how it's done and what symbols are involved for the different ways of finding it. Okay, let's get to it. Hello, and welcome to Chapter 2, Section 3, Measures of Central Tendency. Now that we know how to organize and visually represent data, we want to also be able to supplement the information displayed in our graphs by giving numerical statistics that describe the center, shape, and variability of the data set. So in this video, we're going to learn how to find the mean, median, and mode of a population and of a sample, find the weighted mean of a data set and how to estimate the sample mean of group data, and how to describe the shape of a distribution as symmetric, uniform, or skewed, and how to compare the mean and median for each. Let's get started. A measure of central tendency is a value that represents a typical or central entry of a data set. The most common measures of central tendency are mean, median, and mode. So we'll talk about them one at a time in detail, beginning with the mean. The mean is often referred to as the arithmetic average. It's the sum of the data entries divided by the number of data entries. Notation-wise, we use the uppercase Greek letter sigma to denote the idea of a sum, which again means to add things together. We read this as the sum of all x, or to add all the data entries in the data set. The notation for population mean looks different than the notation for sample mean. Remember when I said a few sections ago that you should start looking at notation? Well, you're definitely going to see some of it in this section. Here's the first bit. I would highly recommend, if you haven't already done so, starting a special section in your notebook or the last page of your spiral or something, a space devoted to notation. You'll want to keep these straight and they're going to add up quickly. In fact, if you want, pause the video now and find a piece of paper or a spot in your notebook for notation and start that habit right now. Just as a side note, you may want to do that for calculator notes too, as we'll be going over calculator instructions on these videos every once in a while, and you'll want to be able to refer to your notes easily. Okay, you ready? Back to the current formula. Remember that the population is the entire group of responses, counts, or measurements being considered, and that the sample is a subset of that population. Well, that distinction becomes more important now because we will begin to use different formulas for different data sets, depending on whether the context of the problem refers to the population or the sample. The population mean is represented by the lowercase Greek letter mu. That's how you pronounce that. It kind of looks like a cursive U with a little tail at the beginning, and it's pronounced mu. It is found by adding all the population data entries together and dividing by the total population, represented by a capital letter N. The sample mean is represented by a lowercase x with a bar over the top, which we simply call x bar, and is found by summing all of the sample data entries and dividing by the sample size, represented by lowercase n. So what is the difference in these formulas, and why do we need two of them? Well, the values in the denominator are the biggest part of that, because the population and sample are not the same size. These are completely different numbers. You'll want to make sure you're using the correct formula for the right context. I'll pause for a moment for you to get these descriptions down. Let me walk through a quick and hopefully simple example. Let's say my school has 30 classrooms and there is some value for each classroom that I want to measure. Let's say number of chairs. In order to find the mean of the entire population, meaning the whole school, I would need to add up all of the numbers of chairs for all 30 classrooms, then divide that number by uppercase N equals 30. But if I take a sample of that population of, say, 5 classrooms, I only need to add up the number of chairs for those 5 classrooms and divide by lowercase n equals 5. So clearly the average of the population is not the same as the average of the sample. So when you see mu, you know that you're finding the average of the population, and we'll be using the population size and using the notation mu for population mean and capital letter N for population size. And when you see x bar, you know that you're finding the average of the sample, and we'll be using the sample size and using the notation x bar for sample mean and lowercase n for sample size. I hope this example has helped you see why these formulas need to be different and how important it is to keep the notation straight. Okay, let's talk about two other measures of center, then we'll do some practice problems. The median refers to the value that lies in the middle of the data when the data entries are ordered. Essentially, it measures the center of an ordered set by dividing it into two equal parts. One important note to make about the median is that it may or may not be an actual entry of the data set. If the data set has an odd number of entries, then the median is the exact middle number of the data set. But if the data set has an even number of entries, then you will need to take the two middle numbers and average them or find their mean. The last measure of center that we'll discuss today is the mode. The mode is the data entry that occurs with the most frequency. If no data entry repeats within the set, then there is no mode. If two entries occur with the same greatest frequency, then each entry is a mode and the data is bimodal. Let's do some practice problems. The weights in pounds for a sample of adults before starting a weight loss study are listed. What is the mean, median, and mode weight of the adults? Pause the video and see if you can come up with the mean, median, and mode without looking at your notes. It's pretty easy to find that the sum of the weight is 1,810. We just added all of those together. To find the mean weight, divide the sum of the weights by the number of adults in the sample, which is 7. This gives us a mean weight of the adults of about 258.6 pounds. Now let's find the median. First, order the data. Once you've done that, you simply figure out if you have an odd number or even number of entries to determine if the median will be an actual data entry or the average of two middle entries. In this case, there are 7 data entries, so the median is the exact middle, or the fourth data entry, 268. The median weight is 268 pounds. What about if the adult weighing 285 pounds decides not to participate in the study? What is the median weight then? Well, we still have the data in order, just without the 285 now. We have 6 entries now, so the median is not going to be one of the entries. We need to find the two middle entries and average them. So the median is the mean of 235 and 268. We add them together and divide by 2. We'll get 251.5. So the median weight of the new data set is 251.5 pounds. What about mode? Well, since we have them ordered for the median, it's easy to see if we have repeated numbers. There are 2 entries of 235 and no other repeats, so the mode is 235 pounds. Excellent. Now let's talk about the advantages and disadvantages of using the different measures of center. Let's talk about the mean first. The mean is a reliable measure because it considers every entry, but it has the disadvantage that it is greatly affected by outliers, or data entries that are far removed from the other entries in the data set. The median also considers every entry of the data set, and it's not affected by outliers. However, it is quite time-consuming to order a very large data set by hand. What about the mode? Well, an advantage is that the mode is the only measurement available for categorical data. But if the mode happens to be an outlier within quantitative data, it won't represent a typical data entry. Just as a quick demonstration of how mode is used in categorical data, imagine at a political debate, a sample of audience members was asked to name the political party to which they belong. Their responses are shown in the table. What is the mode of the responses? Well, mode means the data entry that occurs with the most frequency. So that would mean the category that received the most responses. When we order them according to frequency, the response occurring with the greatest frequency is Democrat. So the mode is Democrat. In this sample, there were more Democrats than people of any other single affiliation. Okay, time to do some on your own. Take a look at this table that shows sample ages of students in the class. Find the mean, median, and mode of the ages. Are there any outliers? Which measure of central tendency best describes a typical entry of this dataset? The mean is approximately 23.8 years. The dataset has an even number of entries, so the median is the average of the two middle entries and comes out to be about 21.5 years. The mode is 20 years, which is the entry occurring with the greatest frequency. So which one is the best measure of center? Sometimes a graphical representation can help you decide which measure of central tendency best describes the data set. First, notice how the outlier of 65 pulls the mean higher than the other measures of center. The influence of that outlier makes the mean the least reliable measure of a typical data value. The mode in this case exists, but it doesn't appear to be a typical value as it represents the minimum. Now the median, on the other hand, isn't affected by outliers, and it appears to be right in the middle of the bulk of the data set. So the median, in this case, is actually the best measure of center for the data set. Sometimes data sets contain entries that have a greater effect or a higher significance on the mean than other entries do. You're experiencing this situation right now, in fact. Many courses at the college are designed to have weighted averages where certain categories are weighted to be worth more. So things like exams or quizzes are worth more than other categories like attendance. To find the mean of such a data set, there's a particular formula. The weighted mean is given by multiplying each entry by its weight, and then summing those products together, then dividing the sum by the sum of the weights. Let's do an example. Your grades last semester are in the table. The grading system assigns points as shown. A is worth 4 points, B is worth 3 points, and so on. Find your grade point average. Your grades are the data values. The credits each class is worth are the weights. So row by row, we multiply the points associated with each grade by its weight. Then we sum up the products and weights independently. Then we divide the sum of the products by the sum of the weights. And it turns out that last semester, your grade point average was 2.5. This is an example of a weighted mean. By the way, this is one of those formulas that you want to make sure you put in your notation notes. This one is called the weighted mean. Okay, now here's another interesting scenario. What if you need to find the mean of a data set, but the only thing you're given is the frequency distribution? You only know how many data entries fall into each class, but you wouldn't know what those exact values were to begin with. It turns out that we can still approximate the mean by using the midpoint and the frequency of each class. That is, the mean of a frequency distribution can be approximated using this formula. X bar is the sum of the products of the midpoints and frequencies of each class divided by the sample size. Make a note that in this formula, the X are the midpoints and F are the frequencies of a class, and N is the sample size. I'll review the steps, then we'll go over an example. First, you need to find the midpoint of each class. You do this by adding the lower limit to the upper limit and dividing by 2, and you do this for all classes. Then you find the products of the midpoints and frequencies and find the sum of those products. Then you find the sum of the frequencies. Lastly, you divide the sum of the products by the sum of the frequencies. Let's reuse a data set that we've seen before and see how this works. The frequency distribution shows the cell phone screen times in minutes for 30 U.S. adults on a recent day. Use the frequency distribution to estimate the mean screen time. Using the sample mean formula, the mean screen time is 285.5 minutes. Compare this with the estimated mean. So now if we use this new formula, we use the midpoints that we already had and frequencies to find the sum of the frequencies and products of midpoint and frequencies and the sum of those products. Using this formula, we get an estimate of about 287.7, which is actually pretty close to the actual screen time of 285.5 that we found with the actual numbers. A few other exploratory data analysis terms that help us better describe the data set refer to the distribution's shape. A symmetric distribution is one in which a vertical line can be drawn through the middle of a graph of the distribution and the resulting halves are approximately mirror images. With this type of shape, the mean, median, and mode are all equal and they are located on this line of symmetry. A uniform distribution, also known as rectangular distribution, has equal or approximately equal frequencies for all the classes of entry. Now clearly this type of distribution is symmetric in its own way. The mean and median are again equal in value, but since all the classes have the same frequency, this type of distribution has no mode. The last two types of distributions we'll talk about today are called skewed distributions. A left-skewed distribution has a tail that is elongated more to the left, hence the name left-skewed. When this happens, the outliers towards the left side of the graph pull the mean downward. It actually becomes left of the median. In reverse, a right-skewed distribution has a tail elongated more to the right, and it ends up pulling the mean upwards right of the median. So far, we've been able to categorize a data set by its measure of center and its shape. We're going to wrap up here for now, but next time we're going to talk about how to measure the variation in a sample versus a population. Very good work. I'll see you on the next video.